ladies and germs. So let's talk about specific heat now. This is our next section of this chapter. This chapter won't be terribly long. We'll actually have to test after spring break. So we only got a couple of sections to do. Remember to look at the assignment list posted because, like I said, we're only covering about 2 or 3 lessons a week with maybe a lab, and everything will be due on Friday now, and Friday's like a catch-up day. So make sure you pay attention to that and look at those online e-lesson plans instead of my normal lesson plans. But let's get talking about specific heat. So we gotta first talk about heat and temperature to objects before we talk about specific heat. And what I mean by that is, for example, as you guys know, when a substance absorbs heat energy, temperature increases, right? You know that from cooking things, you know that from when things get hotter from sitting outside, right? It's because they absorb the energy, the molecules in them move faster, which and then, of course, changes the temperature. The temperature is the measurement of the energy of the molecules. And then a number of factors, like mass, for example, actually affect how much of a temperature change occurs. And what I mean by this point is, let's say we have like 2 pots of water, right? Here's one pot of water. Here's another pot of water. I got some heat applied to both. Let's say this one is only half filled, and this one is fully filled with water. All right, so both of these have water in them. Shade in blue. Okay. But let's say I heat both for 5 minutes. Okay. And after 5 minutes, I want to know which one will actually have a larger temperature change. Okay. They both have the same amount of heat being provided. They both are being timed for the same time, but one has more water than the other. And if you actually did this, you would find out this one would have a larger temperature change because there is less water to boil, right? So there's less of it to actually boil. There's more of it than essentially actually absorbing all the heat going in it, so the temperature will increase faster. This would actually start to boil quicker than this one because since there is more, it requires more heat, which I mean, you guys have seen this if you've ever cooked before, right? The more water you add, the longer it takes to cook if you have the same amount of heat applied to it, unless you want to add more heat. It's this type of thing that we're going to be looking at now and looking at why this actually happens. And what we're going to call this idea, okay, is specific heat capacity or just specific heat. They're both the same thing, which is just a measurement of amount of energy needed to change the temperature of a substance. Okay? So when we look at what specific heat capacity will actually measure, okay, if we're looking at the amount of energy, okay, the amount of energy we're going to call what's called joules. Okay, you might have learned this in physical science or back like in 8th grade, 9th grade science, okay, or 8th grade science, sorry. But this is called joules, and we'll abbreviate that as J, right? And then temperature is what we're going to use, obviously, as degrees Celsius, okay? But it's not just these two things we're going to be looking at because we also just saw mass also plays a difference, okay? So mass also plays a difference in how much energy change actually occurs. So when we look at specific heat, which we will call with an abbreviation of capital C and then subscript P, specific heat. That's going to be the measurement of joules, the amount of energy, divided by the amount needed to raise 1 gram of substance per 1 degree Celsius. Okay, so it's going to be joules over grams times degrees Celsius. Because that means, like, for example, it would take however many joules of energy to raise 1 gram of substance per degree Celsius. A good example of that is the specific heat of water, which is 4.184. That's something you should ingrain in your head. Joules per degree Celsius. That means it takes 4.184 joules to raise, whoops, undo that part. to raise 1 gram of water to 1 degree Celsius. So if I want to heat 1 gram of water by 1 degree Celsius, I need 4.184 joules. That's what specific heat actually means. All right, well, so again, let's look at specific heat a little bit more then. So we also have an equation dealing with this. So again, we talked about specific heat, CP is joules per gram degree Celsius. And how we can use this is looking at the amount of energy, actually. Okay? What I mean by that is we're going to look at the amount of energy. So we're going to label Q as energy in joules, okay? Equals, we're going to use M, the mass. We're going to use CP, the specific heat, times delta T. So Q equals MC delta T. Remember, Q means the amount of energy in joules. This means mass. This is our specific heat, like we just talked about. And delta T, that means the change in temperature. So change in temperature. And how we'll measure that is we're going to take the final temperature, T final, minus T initial. So whenever we talk about temperature change, it's always final minus initial for right now. But this is the equation that we will use for this part. Q equals MC delta T. So let's look at how we could actually use this real quick. So what is the temperature change of a 120 gram piece of aluminum whose specific heat is 1.89 joules per gram degree Celsius after 1800 joules of heat energy is applied? So we know when we do specific heat, we have our equation that we just did. Q equals MC delta T, CP. Okay. So if we're talking about 1800 joules of heat energy is applied, that is going to be our Q, because that's just joules, remember. Q is just always joules. We have our mass. Now remember, the biggest thing, guys, is you see this mass is in grams. And your specific heat capacity is in joules per gram degree Celsius. This determines what everything needs to be in terms of units. Like, for example, if this said kilojoules, you can't just plug it in here because this is measured in joules. You have to have them both in joules. Your mass has to be in grams, like not kilograms. Your temperature has to be in degrees Celsius, not Kelvin. Okay? So those type of things you have to keep an eye out for. So this will tell you all the units you need, basically. But going back to this equation, we know the mass now is 120 grams. We have our specific heat given to us, 1.89 joules per gram degree Celsius. And then we're looking for that temperature change, delta T. So we're just looking for the whole change in temperature. So what the magnitude of it is. So what we're going to do now is just solve for delta T. So we'll multiply these two together, divide them over by 1800. And the temperature change that we should get when that amount of heat energy is applied is about 7.93 degrees Celsius. That's pretty much it. Okay. Let's look at another one. Let's say heat energy equal to 25,000 kilojoules is applied to a 1200 gram brick, whose specific heat is 2.45 joules per gram degree Celsius. What's the temperature change of the brick? So we're going to use Q equals mc delta T, and we're solving for, again, that change in temperature. So let's plug in everything. We know it's 25,000 joules. Our mass is 1200. We have the specific heat of the brick. Now we're just trying to figure out delta T again. So again, we'll multiply these two together, divide them over. And now we should get the temperature change to be about 8.5 degrees Celsius is how much it'll change by. Okay. That's pretty much it, okay? You have to know what this equation means and everything else with it. So we'll do one more quick one, right, with this. So now, it's the same brick now. Same energy is being applied, same mass of the brick, same specific heat. Specific heat won't change between substances. But now I want to see if the brick was initially at 25 degrees Celsius, what's the final temperature? So again, let's go back to Q equals mc delta T. And like we said, this delta T was the T final temperature minus T initial. So now we have to break this down even more to how to solve for it. So we have the same energy still being applied, 25,000 joules. The mass is the same. The specific heat is the same. But now we want to find out the final temperature. So we're finding T final minus, and we have it initially, 25 degrees Celsius. So now we got to solve for T final. Lots of ways you could do this, right? One way is let's take 25,000. Let's multiply these two numbers together. You should get 2,940 times T final minus 25 degrees Celsius. And you could do two things here. You could distribute it through, or you could just divide 2,940 over, which that's what I'm going to do. It's a little bit easier. Which from the last problem, you know that temperature here is 8.5. Equals now T final minus T initial. Now you just got to add 25 over. T final is 33.5 degrees Celsius. Which again makes sense. Your T final should be higher right now because you're applying heat to everything. Okay, you're not taking away heat. We're not going to talk about that yet. But all this, you're applying heat to it, or it's required. But again, the whole homework deals with basically this equation, okay, which then your homework is going to be SP5 in the Flexbook. It's only about 6 straight problems that all deal with this equation, really. Okay. So any questions, let me know.